Nisarg is an assistant professor at University of Toronto in the Department of Computer Science. He was formerly a postdoc at Harvard Center for Research on Computation and Society. He has a PhD from CMU. And he's got a number of high-profile honors, such as the Victor Lesser Distinguished Dissertation Award from the International Foundation for Autonomous Agents and Multi-Agent Systems, and a Facebook Graduate Fellowship. So the less formal bio piece is that I discovered his work while on the Faculty Affiliates Committee, which I served on for a couple of years. And I think that was a real perk of being on that committee, is meeting new people and learning about their work. And I think his work is really fantastic. He's working at the intersection of computer science and economics. And what's great about his work is that he's also been, one of the great things, many great things about his work, but I also appreciate he's developed some free online tools, some of which I am quite interested in using myself in certain circumstances. But I made the mistake last time of naming those tools and telling about them. So I'm not going to do that this time. I know he's going to tell you about those tools. So I'm just going to hand it over to him and let him give the talk. So welcome, Nisarg. He's a faculty affiliate, so don't really need to welcome him, but thanks for coming and giving your talk.
Thanks, Graham, for the wonderful introduction. And sorry that you have to hear this talk for.
Oh no, I think we lost Nisarg just as he was about to do his talk. Unfortunately, our speaker got frozen and disconnected, so we believe he's trying to reconnect. So just bear with us. Oh, I just saw him pop up.
Okay, so sorry everyone for that interruption. Somehow my internet just completely went away and I can't seem to get it back up. So I'm currently sharing my mobile's hotspot. I'm doing the hotspot, and so my internet might be a bit choppier, but hopefully it will get us through this hour. And hopefully I won't run out of data. All right.
You're just chatting about that. So far so good. So go for it.
Okay, sounds good. All right. Okay, so I'm guessing that you guys can see this.
Yeah.
All right, perfect. Okay, so right. So as I was saying that the purpose of this talk is to give you an overview of this kind of preference-based fairness notions that are coming up from the literature at the intersection of computer science and economics. And so in the first part of the talk, I'll explain the context of where these notions are coming from. And I'll describe our recent work in this fair division literature. And then in the second part of the talk, I'll try to convince you that these notions are also quite applicable in machine learning settings. Okay. So as you all know, these algorithms are making decisions in various scenarios nowadays, from deciding who gets loans or bails to deciding which ads to serve or whom to hire. And even in some high-stakes scenarios, such as whose organs should be donated to whom. And because of this, there has been a recent surge of interest in trying to make sure that these algorithms are in fact making these decisions fairly. And this surge has partly been fueled by some popular accounts where the algorithms were seen to be making these decisions in an unfair manner. So this, while fairness is a recent subject of interest in the machine learning literature, it has been studied for almost a century in this literature on social choice theory. And this is the paper that originally kind of jump-started this literature titled The Problem of Fair Division by Hugo Steinhaus in Econometrica in 1948, which he allegedly wrote while hiding from kind of the aftermath of World War II. But so this paper tackled the problem which is now known widely as cake cutting. But later, computer scientists got interested in the subject, and that gave rise to this field of computational social choice, where we use algorithms to make these kind of collective and fair decisions. And the one thing that I like about this field is that it doesn't just talk about fairness in algorithmic decision making. Fairness is only treated as one of the aspects that you want to consider. The other being, for example, how do you elicit the preferences of the users that are impacted by these kind of decisions? How do you make sure that these decisions satisfy some kind of economic efficiency notion? How do you set the incentives right? So for example, when you are eliciting the preferences, does your system provide adverse incentives for agents to lie about their preferences in order to get a better outcome? And one aspect that I've listed here, which is only getting more traction recently, which is ethics. And I think ethics is still very less explored compared to the other aspects that I've shown here. And one thing I want to say is that I'm going to keep the talk at a very high level. I'll try to include as little math as possible. But at the same time, one thing that I want to convey is that the fairness notions that come out of this literature are very concrete and lead to some very interesting theoretical research questions. So in today's talk, I'll focus mainly on three of these aspects: fairness, efficiency, and incentives. And I'll probably skip the incentives part just to kind of stay on time because of the early technical difficulties. So based on these concepts, the literature offers very compelling solutions to a number of different problems. And so back in 2014, my collaborators and I thought that it would be cool if we just take some of these very compelling algorithms, which give these provably fair solutions, and just deploy them onto a website where people can just go to this website and then try these instances out and then get fair solutions to their everyday dilemmas. And so currently, Split offers solutions to 5 different everyday tasks. So one is share rent, which is where a group of, let's say, 5 roommates, they get together and they rent an apartment, and the apartment has $4,000 a month rent because you are in Toronto. And now they need to decide which roommate will stay in which bedroom and how much rent he or she should pay. And so this application basically aggregates the preferences of these users and comes up with a provably fair solution. The split fair application basically comes into play when you are taking a cab together, but you are dropping off at different locations, and now you need to decide what share of the total cab fare you should pay. And the assigned credit application is when you do work as a group and you need to divide credit between the different people. So for example, if you write a research paper together, then each person can say what they think was the relative contribution of the other group members. And then Split would aggregate all these reports to come up with kind of the fair credit assignment to each individual author. But really the domain where this has gotten really popular is teachers who love to have their students who are working in group projects use this application, and that's how they assign the grades to the students rather than giving the same grade to everybody who was in a group project. The application that I'll focus on today is this divide goods application, where you just have a bunch of goods that you want to divide between a bunch of people. And the distribute tasks is the opposite application, where the items that are being divided are chores that you don't want to be assigned to yourself. And Split has really gained popularity. So over the past 6 years, more than 200,000 people have used it for solving real world problems. So this divide goods application that has a number of different real world settings where you can use them. And here I've listed some of them based on the feedback from the Split users who have used it for something like estate division or divorce settlement, but also a group of friends who bought season tickets for some baseball games and they divided the tickets to the individual games between the individual friends. Or a team of gamers who found some loot while roaming around collectively and now want to divide this loot between the individual gamers, or art collectors splitting some collectively bought artwork. So the key aspect of this application is that each person may have a different kind of valuation over the different items. Okay, so I might think that one item is more valuable to me, but you might disagree and you might have a different value for that same item. And here, the algorithm that we deployed back in 2014 when Split was launched wasn't very compelling. It didn't really give very strong fairness guarantees. And so we started receiving a bunch of complaints. And here is one such complaint from a group of 4 brothers who wanted to divide an inheritance of some 30+ furniture items using Split. So one of the brothers went onto the website and he was trying it out on a bunch of instances. And he realized that on some of the instances, the algorithm's outcome wasn't really something that he would consider fair. So he went ahead and created a minimum working example. And here is the minimum working example that he suggested. He said, imagine that we have 3 people and we have 5 identical candies we want to divide between them. So what can you do? Well, the fairest allocation that you can do is to give 2 candies to 2 of the people, and then a third person would be left with a single candy. You can't really be any fairer than that. But to his surprise and to our surprise, Split actually gave 3 candies to the same person, and then the remaining 2 were left with a single candy each. So we dove into this issue and then we found a better solution. But before I describe all that, I just want to briefly describe the setting that we are working with. So in this setting, we have a number of, we have basically this so-called valuation matrix, where the columns are the different items that you want to divide, and the rows are the different agents who want to receive these items. And each agent has a value for each item, and the values are additive. So for example, if you give this boy at the top the painting and the car, then his value would be 67 plus 150. And now these items are not divisible, they are indivisible. So you can't really break that item and give different parts to different people. You have to take each item and give it in whole to one of the three people. So a bit more formally, I'm going to denote by capital N a set of N agents, okay, by capital M a set of M, this indivisible goods. And these agents will have some valuation function VI. This denotes their preferences, and they will assign basically a non-negative value to every possible bundle of goods that the agent can get. And as I said, the valuations are going to be additive. So the value for a bundle is simply the sum of the values of the individual goods in the bundle. And our goal is to come up with an allocation, which is simply a partition of the items between N bundles, where AI is the bundle that is then given to agent I, for which the agent has value VI of AI. Now, in this literature, the gold standard notion of fairness is called envy freeness. And envy freeness basically says that once you create your allocation, nobody should envy the allocation given to somebody else. So if you look at any pair of agents I and J, the value that agent I places on her own bundle AI should be at least as large as the value that agent I places on the bundle that is given to agent J. So agent I shouldn't envy agent J, vice versa, J shouldn't envy I as well. And this should hold for every pair of agents. So everybody should feel that they got the best cut out of the whole set of items. But when you have goods that are not divisible and you can't charge payments to agents, you can't really guarantee this. Imagine that you have just one item and you have two people. Whoever gets that item is going to be envied by the other person. So in this case, our old mechanism relied on a bunch of kind of weak relaxations of this envy freeness notions. And when we looked through the literature, we found this very nice and strong, very compelling relaxation of envy freeness that's called envy freeness up to one good. So here you say that, look, I can't really prevent agents from envying other agents, but at least if agent I is envying agent J, I should try and limit that envy. And one way to do that is to say that there should be some good. There should exist a good in agent J's bundle, such that if agent I ignores that good for a moment and just looks at the rest of the bundle, then agent I wouldn't envy the rest of the bundle. So in that sense, agent I's envy for agent J is limited to that one good that agent J has received. So this kind of a minimal relaxation. And the good news is that if you just want to achieve this relaxation, you can achieve it very easily using a polynomial time method that is probably already used kind of very heavily worldwide. And this is called the round robin procedure, where you line up the items in, on a table and you line up the agents in a cyclic order. So if you have three agents, let's say blue, orange, and green, then you have blue, orange, green, blue, orange, green, blue, orange, green, and so on. And now the agents take turns in this cyclic order. And in each turn, the agent would pick the item that is still available on the table that she likes the most. And so the blue agent goes first, picks a painting that she likes the most. Then the orange agent goes, picks a painting she likes the most, and so on and so forth until all the items are gone. Now, I want to very briefly convince you that this allocation would always satisfy this EF1 notion. So let's look at why the green agent, for example, wouldn't envy the orange or the blue agent up to some one good in their bundle. And the argument would be very similar for other pairs. So what I'm going to do is I'm going to divide this allocation into phases, where the first phase starts from the first time that the green agent picks an item. The second phase starts when the green agent picks an item for the second time. The third phase starts when the green agent picks an item for the third time, and so on. And notice that within each phase, the green agent goes before the blue or the orange agents. So the green agent must like the painting that she picked at least as much as the paintings that the blue and the orange agent picked afterwards. Okay? Because if she wanted to pick any of these two paintings, she could have picked that, but instead she picked the painting that she indeed picked in that phase. So within each phase, the green agent doesn't envy the other agents. And because of additivity of valuations, even across all the phases combined, the green agent wouldn't envy the other agents at all. So the only reason that the green agent envies the blue or the orange agent is because of these first two items that they picked before the green agent even started picking an item. So in particular, if you ignore this first item that the blue agent picked, then the green agent wouldn't envy the blue agent for the rest of the items that he has. And if you similarly ignore the first item that the orange agent picked, then the green agent wouldn't envy the orange agent for the remaining items. Okay, so this is great. It's a fairness notion that is pretty compelling. And note that in the previous instance that I mentioned, it would indeed solve the problem of one agent getting 3 candies. Because if one agent gets 3 candies and another agent has only 1 candy, then this would not be EF1. The agent with 1 candy would envy the agent with 3 candies, even if you ignore one of the candies. However, the problem is that this allocation procedure is not very efficient. And here I'm referring to a very basic notion of economic efficiency called Pareto optimality. And this says that once you do your allocation, I shouldn't be able to come along and propose a different allocation, just completely reshuffle all the goods such that all the agents are happier. And it turns out that this round robin method, because it's a very greedy method, it's a very local method, it violates this notion of efficiency. Once you have your round robin allocation, you can in fact reshuffle all the goods such that everybody's happier with the new allocation than with the old allocation. So that led us to this question back in 2016, which is whether there always exists an allocation that is both fair in the sense of being envy-free up to 1 good and efficient in the sense of being Pareto optimal. And the answer that we found was yes, you can indeed, there always exists such an allocation. And in fact, if you find the allocation that maximizes the product of the values that the agents have, then this would satisfy both these properties. Yeah, so as an example, if you have these 3 items and these 2 people, and if these are the values that this boy places on the 3 items, and these are the values that this girl places on the 3 items, then what you want to do is you want to find a way to assign each item to one of the 2 people such that the product of their total values is maximized. And in this example, it turns out to be this allocation where the guy has value 5 and the girl has value 4 plus 5, which is 9, and the product of 5 and 9, which is 45, is the highest possible. So I won't walk you through the proof of why this satisfies both these notions, but we prove that computing this allocation would always guarantee both this desiderata. Now, one thing that I haven't talked about is how do you actually compute an allocation maximizing the product? Because first of all, we are doing a discrete optimization, not even a continuous optimization. And then this objective function is highly nonlinear. So for that, this problem is indeed NP hard and even APX hard. But we have an integer linear program that works reasonably well for instances of kind of real world size. So even if you have like 10 users and 200 items, you can compute this outcome in less than 30 seconds, which works reasonably well for split it. Okay, so then back in 2015, we deployed this algorithm to split it. And since then, we haven't really received any complaints regarding unfairness of the algorithm's outcome. So in the absence of any formal study regarding user satisfaction, this is the best indicator that we can have that the users are liking this allocation procedure. And one nice thing about this procedure is that you can actually explain this envy-freeness and Pareto optimality guarantees to lay users in a very easy manner. And this is something that I'll touch upon towards the end of the talk. Okay, when I talk more generally about explainability. All right. One thing that I want to point out is that this literature offers almost as many open questions, challenging open questions, as it offers compelling results. So, for example, I talked about this MNW allocation satisfying these 2 properties, EF1 and Pareto optimality. And I mentioned that this is an NP hard problem to compute an MNW allocation, but one might ask if you can compute a different allocation that is still EF1 and PO in polynomial time. And so this is an open question. There was some partial progress made in 2018 when one group of authors showed that this is at least computable in pseudo polynomial time, which, by the way, you cannot even compute the allocation maximizing the product in pseudo polynomial time because it's strongly NP hard, not just NP hard. Another open question that stemmed from this work is this regarding this stronger fairness notion that we call envy freeness up to any good. So remember that in envy freeness up to one good, I say that agent I shouldn't envy agent J if you hide some good from agent J's bundle, if you ignore some good from J's bundle. This stronger notion says that if you ignore any good from J's bundle, that should be enough to eliminate the envy that I has for J. Okay, so the envy that I has for J should be limited to even the least valuable good in J's bundle according to I. So there's just a difference in quantifier here. And for this, it's an open question whether an allocation satisfying this stronger fairness guarantee always exists, even if you forget about Pareto optimality. And there was a paper in 2020 in EC, which is kind of the premier conference for research at the intersection of computer science and economics. And this was the best paper in EC 2020, which showed that such an allocation always exists when you have 3 agents. But for more than 3 agents, this is still open. All right, so we deployed this back in 2015 to split it, and then we were all happy because we weren't really getting any complaints anymore. And then last year we started thinking about whether this fairness guarantee that our algorithm provides, whether that is good enough. And then we realized that this fairness guarantee of EF1 is not really good enough. And here is an example that demonstrates that. So in this example, you have 4 agents. You have a circle agent who likes circle goods. So he has value 1 for the circle goods and 0 for the square goods. He doesn't really want the square goods. The square agent is the exact opposite. He wants the square goods, but doesn't want the circle goods. And the flexible agents, these remaining 2 agents, they want all goods. Okay? They have value 1 for everything. And consider the allocation where each flexible agent gets a circle good and a square good. Now, in this allocation, I'm claiming that this is EF1. Note that the circle agent does envy the flexible agent, but if you ignore that one circle good, then he wouldn't envy the rest of the allocation that the flexible agent has because he doesn't really care about the square good. Similarly, the square agent doesn't envy the flexible agent if you ignore a square good. So even though this is kind of envy-free up to one good at this individual level, I'm claiming that this is not fair even approximately at the group level. So if you consider this group of 2 agents, the circle and the square agents, and the group of these other 2 agents, then this group S envies this group T very significantly. And the way I'm thinking about this is that if group S were to take the resources given to group T and then redivide it amongst themselves the way they want, then they would have given the 2 circle items to the circle agent and the 2 square items to the square agent. So they would not only be better off by 1 each, but they would be better off by 2 each. Okay, so in this sense, the fairness is violated at the group level by more than just 1 good. Okay, it's violated by at least 2 goods here. And you can create even worse and worse examples if you want. And even though I don't need to preach to this community the importance of fairness at group level, I want to just say that this group level fairness comes up even in resource allocation problems. So for example, if you're a school district trying to divide educational resources between teachers in your district, then you not only want to be fair at the level of individual teachers, you also want to be fair at between teachers of different grades, teachers of different geographic area, teachers teaching different subjects, teachers of different race or gender or ethnicity. So you want to be fair across all these different overlapping sets of groups. And sometimes you may not even have these groups given to you in advance. Okay? So what would be amazing is if you have a notion of fairness that applies to all the possible groups of agents simultaneously without having to consider these groups predefined. And that's the kind of motivation with which we define this notion that we call group fairness in this fair resource allocation context. And I won't go through the formal definition of this fairness concept, but it's pretty much along the lines of what we saw in that example, where you say that you shouldn't have any group of agents S which can take the resources given to some other group of agents T, redivide it amongst themselves such that everybody in S is better off after the redivision than the allocation that they had received previously. But there's one caveat here, which is that I'm not talking about the sizes of the groups S and T. Yes, in that previous example, both S and T consisted of 2 agents each. So the groups S and T were comparable. But if you have a group S consisting of just 1 agent versus a group T consisting of 1,000 agents, then certainly if the 1 agent takes the resources given to 1,000 agents and gives it all to himself, then he would be better off. So what we do is we appropriately scale the utility of this group S members after they redivide the resources of group T by size of S divided by size of T. So if they are looking towards a very large group, then we scale down their utility and then ask if they are still better off. And note that this is an exact fairness notion. This is something that in fact generalizes envy freeness. So this is a group fairness notion that is stronger than individual fairness, unlike in machine learning, where group fairness is usually weaker than individual fairness. But because we can't achieve envy freeness exactly, we also can't achieve group fairness exactly. So we then define a group fairness up to one good notion. And then we show that maximizing Nash welfare actually doesn't just satisfy individual envy freeness up to one good. It actually satisfies this group level fairness up to one good. And if you just want that, and you don't want the Pareto optimality, then you can actually just compute a local optimum of this Nash welfare function, which you can do in pseudo polynomial time. And there's an open question here as well, whether you can compute such a local optimum in polynomial time. All right, so we started from this individual fairness notion, and then we bumped it up to group fairness up to one good. And then we asked again this year whether we are fair enough yet. And the answer was once again no. And the reason is exemplified in this kind of very tiny example again, where you have these three agents, and this time let's say you have 4 identical candies. Note that all the fairness notions that we have seen so far say the same thing. You should give 2 candies to one of the 3 people, and the other 2 people should get a single candy each. This is the fairest thing that you can imagine. Except it's not clear who should get those 2 candies. So for example, if you go to split it, and if you create an instance with 3 people, Alice, Bob, and Claire, listed in this particular order, and then you have 4 identical candies, then split it always gives, no matter how many times you run this instance, it will always give 2 candies to Alice, the person who is listed first in the ordering. So that seems some kind of systemic bias towards one of the agents. And as you can imagine, the only way to really remove this bias is to use randomization. Now, before I go to randomization, notice that this problem wouldn't have arisen, and you wouldn't have needed randomization at all if these candies were somehow divisible, if you could split the candies. Because then you would give 3 candies to 3 people and then split a 4th candy between the 3 people equally. And when you have the ability to randomize, you can kind of recreate that fractional allocation where everybody is getting the same number of candies, but in expectation. But you have to be careful exactly how you randomize, because if you do a bad randomization, and obviously silly randomization, where you pick an agent at random and then give them all the 4 candies, then this in expectation, they would all achieve the same number of candies. So this would be fair in expectation or ex ante before the coins are tossed. But after the coins are tossed, the allocation would be highly unfair. And you don't want this. Obviously, this is a silly example. Really what you should do is just give 1 candy to each person. And then only for the 4th candy, randomly pick an agent to give that 4th candy to. And this would not only be fair ex ante in expectation, but also fair ex post after the coins are tossed. And in this silly example, everything happens to be very trivial because all the goods are identical. But when you have goods that are not identical, then this question becomes much more challenging. So for example, you can ask, as my ex post fairness notion, can I achieve envy freeness up to 1 good, which is something that we have already seen how to achieve. But at the same time, can I achieve ex ante fairness in the form of exact envy freeness? So what that is really asking is, can you always randomize over allocations that are envy free up to 1 good in order to achieve exact envy freeness, to just completely eliminate any envy in expectation ex ante? And this was an open question. So we looked at this question along with a bunch of other combinations of ex ante guarantees and ex post guarantees. And our main result in this paper this year at EC was that there always exists a way to randomize over ex post envy free up to 1 good allocations in order to achieve exact envy freeness ex ante. And in fact, you can do this in polynomial time. We also have some other possibility and impossibility results if you are interested. But again, once again, we have some interesting open questions. So for example, instead of randomizing over allocations that are just EF1, what if I want to randomize over allocations that are both fair and efficient, both envy free up to 1 good? and Pareto optimal. So these are the kind of allocations that are returned by maximizing NASH welfare. Can I randomize over such allocations to achieve envy freeness ex ante? So this is an open question and one of kind of the major open questions that falls out of this work. All right, so one thing that I haven't really talked about throughout the talk so far is incentives. And indeed, all the methods that I described so far create adverse incentives for where people can lie and benefit from lying. Okay, they can get a bundle of goods that they actually value more than the bundle that they would receive if they reported their honest preferences. And the game theory literature offers a very strong axiom called strategy proofness, which if you achieve strategy proofness, then nobody would ever have an incentive to lie. And long story short, just to kind of, in the interest of time, we show that this kind of strategy proofness can be achieved. In fact, it is achieved by maximum Nash welfare algorithm without losing any of the other properties. Yeah, so you still have and group fairness up to one good, Pareto optimality, and you have strategy proofness, and you have, in fact, polynomial time computability, but in this very restricted domain where agents have values either 0 or 1 for each good. Yeah, so each agent either likes a good or doesn't like a good, but they don't have different levels of intensity of preferences. And it's known that if you go kind of beyond this, where agents can have 3 different values for the goods, then you cannot achieve strategy proofness along with any reasonable notion of fairness and efficiency. All right. So that is what I wanted to talk in terms of the context of where these preference-based fairness notions are coming from. Now I want to take the next 10 minutes or so to talk about how these notions can be applied to machine learning tasks such as classification, clustering, or reinforcement learning.
Sure, I'll just pause for a quick sec just for your own planning. I discussed this with Aaron. Given that you were delayed 10 minutes, what we'll do is we'll run it up right till noon. Okay. And then if people need to go, they can leave at noon, but we can take an extra 10 minutes for questions. You'll give just so you can plan for the rest of your time.
That's perfect, because that's exactly where I want to be here, and okay. I don't need to cut any of the material from here on.
Yep, great.
Okay. Sounds good. All right, so let's talk about the fair classification model, because I feel like classification is one of those contexts in machine learning where fairness has been explored the most. And in the standard fair classification model, you have individuals who are represented by a vector of non-sensitive attributes, let's call it X, along with a sensitive attribute A, which basically denotes their membership or the lack of membership to a protected group. And in general, A can also be a non-binary attribute. It can be a multi-class attribute. Sometimes you have this binary ground truth. For example, if you are in a loan application where you are deciding whether to give loan to a person or not, then the binary ground truth can be whether this person is actually going to be able to repay the loan. And your goal is to come up with a binary classification, which ideally should match the binary ground truth, except outside of the training data, you wouldn't have access to the binary ground truth. And this community already knows the standard fairness notions that have been talked about quite a bit in the literature on fair machine learning, things like demographic parity or equalized odds. And the one thing that I want to, so I won't go over the formal definitions of these notions, but one thing I want to talk about is that while these notions generalize very well to non-binary groups, so for example, when the sensitive attribute is multi-class, they don't generalize as easily when the binary classification outcome itself is multi-class. So as a silly example, if you have the loan application, but imagine that instead of just deciding whether to give loan or not to give loan to each applicant, you have the option of giving 5 different types of loan. If you decide to give the loan, or you can decide to not give the loan. So there are 6 different outcomes that you can choose from. And now these individuals, these applicants, also have preferences over which kinds of loans that they want to receive. And so they have a different value for every possible loan type. And then it's not clear how fairness should kind of interact with the preferences that these applicants have over the different loan types. Now, envy freeness very naturally applies to this kind of setting, and it very naturally integrates the preferences of these loan applicants over the different outcomes that they can receive. However, envy freeness is an individual level fairness notion, which is very strong, way too strong for this kind of a task. Okay? Because at the end of the day, somebody is going to receive a loan and somebody is not going to receive a loan. And clearly the person who doesn't receive a loan would envy the person who receives a loan. So what we explored with a group of students, including Safwan, who is also kind of a member of Vector Institute, or at least was, I don't know whether his current status, what that is. So including Safwan, we looked at this notion of imposing envy-freeness on average across the groups. So weakening envy-freeness rather than strengthening it, and only applying it on average. So a bit more in detail, suppose you have a pair of groups S1 and S2, and you want to make sure that this group S1 shouldn't envy the group S2 on average, because S1 isn't really less entitled than S2 in any particular manner. Then instead of saying that no individual I should envy any other individual J, what I would do is I would pick a random individual I from group S1, a random individual J from group S2, and then I would ask that in expectation, there should be no envy going from agent I towards agent J. And you can define kind of extensions of other notions of fairness explored in this computational social choice literature, and you can explore them in the machine learning context, which is something that we do. And the first thing that we observe is that these notions, they generalize the classic demographic parity, equal opportunity, equalized odds, or even this recently proposed equalized financial impact notion in a very basic sense, which is that when you are in the binary classification setting, and when people have 0-1 preferences, basically my utility is 1 for receiving the loan and 0 for not receiving the loan, then you can define the groups appropriately such that these notions boil down to this the classic fair machine learning notions. Okay, so for example, if you want to recover demographic parity, you can define S1 to be the set of agents who have sensitive attribute equal to 0, S2 to be the set of agents who have sensitive attribute equal to 1. And then you can ask that neither group envies the other group. We also noticed that even if you want to achieve this fairness across exponentially many pairs of group, then you only need polynomially many training samples. Once you have that, you are going to get good generalization where low envy on training data would translate to low envy on the test data. Another benefit of looking at this kind of preference-based fairness notions is that they kind of give you a framework to talk about fairness across settings that both have a ground truth, something like loan or bail decision settings, and settings that don't have a ground truth, something like advertising setting where the different individuals just have preferences over what kind of advertisements they want to see, okay, without there being any ground truth. And all you need to do is you need to define the groups appropriately, whether the groups take into account the ground truth or whether they don't take into account the ground truth. We also look at the impact that these kind of fairness notions have on the loss function of the principal. But for more details, I encourage you to check out the paper. Another thing I want to talk about is fairness in the clustering domain. So the ordinary clustering problem is where you want to place k cluster centers among n data points. But again, if you want to talk about fairness, you have to bring in real human individuals somewhere. And so one perspective that gives fairness importance is where these data points represent individuals, and these cluster centers represent locations where some public facilities are going to be built. And these individuals, they want these public facilities to be close to them so that they can access these facilities relatively easily. And the agent is going to be basically accessing the closest facility that is built. Okay, so more formally, as input, you are given the locations of these n agents, some possible cluster center locations, and a distance function d, which is a metric which defines the distances between the agents and the facilities. And your output is a set of k cluster centers, and then the cost to an agent is the distance that the agent has to the nearest facility. And now you want to place these facilities in a way that is fair to all the possible groups of agents at the same time. And so here, the notion that we explore in this work published this year with another student, Evie, who is also on this call. So in this notion, we look at this notion called core. And the core is something I haven't talked about so far in the talk, but it's something that's implied by group fairness. So the core in this particular setting basically says that since you are building k public facilities to serve n agents, every group of at least n over k agents deserve a facility to serve them. If I have a large enough coalition, I deserve one facility to serve my coalition. So if there is a group of agents S of at least n over k size that can find a new location Y such that this location Y is closer to each person in the group than the closest center that they have in the current solution, so then the current cost, then we are going to say that this is a violation of this fairness guarantee. So we shouldn't be, there shouldn't be any group of agents S. Note that there is no restriction based on some sensitive attribute. This applies to all possible groups of agents. There shouldn't be any large enough group that deserve a facility which can place a facility which is closer to each of them than their respective nearest facilities. And then you can talk about approximations of these fairness notions where you blow up the distances that they have to their own proposed facility by some factor alpha, and then ask whether this is still better than the distance that they have to the nearest facilities. And there was a paper published in ICML this year which showed that a clustering that is exactly achieves this core notion isn't always guaranteed to exist. There are counterexamples, but you can always achieve this 1 plus square root 2 approximation. And with EVI, what we show is that if you are in the Euclidean space, which is kind of the more classic setting, then you can improve this approximation ratio to 2. And we also have some computational hardness results and some learning theoretic results in this paper. Right. Finally, I want to talk about fairness in the context of reinforcement learning. And so here, with both EVI and SAF1, we look at this classical stochastic multi-arm bandit problem. So in the classical problem, you have this setting where you have a bunch of arms and you don't know which arms are best. Each arm has an associated unknown distribution. And when you pull the arm, you are going to get a sample reward from that distribution. Okay? And if you knew which arm is best, which arm has the highest mean reward, then you would have just pulled that arm repeatedly. But since you don't know which arm is best, you start pulling different arms, and then you measure your regret compared to pulling the best arm repeatedly in hindsight. So again, if we want to introduce fairness to this problem, we have to have multiple agents, and where kind of we have some kind of trade-off. So what we look at is we look at a multi-agent version of this multi-arm bandit problem, where the arms are some kind of policy decisions. And when you pull an arm, you don't just get one reward from one distribution, but there are n different agents being affected by this policy decision, and each agent observes a different reward from a different distribution. So there is a distribution for every arm I and every agent J. And you don't know all of these distributions from the start, and you start putting different arms, and you want to converge to not the best arm, because there is no longer any notion of a best arm. Each agent might think a different arm is best for them personally, but you can still define what is the fairest arm by using this Nash welfare notion, which maximizes the product of the utilities of the agents. And you can also define the fairest distribution over arms. And so what we show is that you can learn this kind of fair policy by starting to pull arms with vanishing regret, where the regret is now measured in terms of the Nash welfare that you are losing out. All right, so that's the technical part of the talk. I just want to take maybe 5 minutes or so to convey some high-level takeaways. So there are two main takeaways I want to focus on. One is that there is a very nice feedback loop between deployed applications like Split and this theoretical research foundational work, which is that these deployed applications are based on this theoretical research, but in turn, feedback from users from these deployed applications also gives rise to new theoretical research. So for example, and this can happen in two different ways. So users sometimes point out problems with existing algorithms, as it happened with this divide goods application, which led us to discover this maximum Nash welfare solution. And sometimes they point out novel real-world domain where this kind of fairness is required. So to give you an example, back in 2015, a representative from one of the school districts in California reached out to us and pointed to this problem of allocating unused public school facilities to local charter schools in the area. And there is actually a Proposition 39 in California, which mandates that this has to be done without any exchange of money and in a fair manner. But the law doesn't really specify what fair means. So we worked with this representative. We figured out what kind of fairness notions would be interesting for this domain. And then we designed an algorithm that is provably achieves these fairness notions. The other takeaway I want to mention is explainability. And one thing that I've really liked about working in this field is that notions like NV freeness can be explained to end users very, very easily. And this has been one of the greatest selling points of Split. So for example, in the divide goods application, after the algorithm comes up with the division, it provides an explanation to each user, which goes something like this. It says you assigned a total of 635 points to the items that you were assigned. In contrast, you only assigned something like, let's say, 365 points to the item that this other person was assigned. So therefore, you don't envy this other person, and therefore you should be happy. And sometimes you won't exactly have envy freeness. Then you can explain that at least if you ignore this one good, then you don't envy them. And people have really liked kind of seeing this kind of fairness explanations based on the feedback. Okay, I want to end on describing a few kind of high-level future challenges. So one is to extend the study of these kind of fairness notions to other domains. I already talked about this charter school resource allocation domain. We have also had some recent work on looking at the issue of gerrymandering or political redistricting through this preference-based fairness notions lens. And we have also looked at something called participatory budgeting through the same lens, where residents of a city vote over how the public budget should be allocated to different public projects. Another important challenge is to incorporate the excess of time into these fairness notions, because these are all static fairness notions, whereas in practice, most systems have users interacting with the system over time. Another challenge that I'm really interested in is some interplay between fairness and incentives. So there is this popular widespread belief that in their drive to make the treatment equal between the protected group and the non-protected group, these fair algorithms might be giving an unfair advantage to the protected group, and this might cause some incentive for members of the non-protected group to lie and say that they are actually members of the protected group. And I was reading a news article a few months back where a mom was arrested because she lied on her son's college application and mentioned that her son is both Black and Latino, a mixed race, when her son was really white, because she thought that this would give her son a leg up in the college application process, which she believed uses some kind of fair admission process. So I have an ongoing work with Safwan, where we are looking at this problem of kind of what happens when you impose fairness. Obviously, unfair algorithms give incentive for Black people to misreport themselves as white people because they give unfair advantage to white people. On the other hand, fair algorithms give incentive for white people to misreport themselves as Black people. And so what is kind of the level of these two incentives and how do they compare? So this is still preliminary and ongoing work, but one of our findings is that the choice of the fairness notion that you impose is very critical. Some fairness notions do seem to give create more adverse incentives than some other fairness notions. All right, and here is a shameless plug about our other not-for-profit endeavor, robovote.org, which is not for resource allocation problems, but rather for voting problems. So if you want to decide where to go for lunch after COVID ends, obviously, then you can decide it using this website. So if you haven't seen this before, I encourage you to check it out. And here are the references in case you are interested in exploring them later on. Okay, that's it. Thank you, everyone, and sorry for all the technical difficulties early on.
Thanks a lot, Nisarg. So it was a pleasure to see the talk a second time. So it's fantastic to have you here. And if anybody needs to go right at noon, I know some people will have appointments, different things that they're off to. You can just slip out, no problem. But we will stay around for about 10 more minutes till 10 after to take some questions. I will kick it off with a non-scientific question. I am curious, in developing Split It and also RoboVote, which you told us about the end, you made a decision to go the not-for-profit route on both of those. And you're also working with multiple people who might have some stakes. So walk us through that question or the decision-making process. Were some people pushing to commercialize it? Was everybody on board for nonprofit?
Yeah, I think everybody was on. I mean, there was some discussion around this exact issue because obviously this discussion would always come up, but I think everybody was on board with the not-for-profit route because the first thing to make sure is that people outside of the community, first of all, we need to make sure that they know about the fact that these kind of algorithms exist, and we need to show that people are actually using these algorithms, right? because otherwise, I mean, we are already getting salaries as researchers, so we are not kind of interested in the monetary aspect just by itself. The greater impact that we can have is when lots of people use these kind of applications, and that can only happen through a non-monetary route. The other thing is that this is an application where the costs are pretty low, right? We are not, unlike many of you machine learning researchers, we are not running some very large scale deep neural network on Amazon cloud computing servers with kind of lots of costs. So this is something that actually Amazon has been very generous so far. They have covered all the costs of Split and RoboBot so far using one of their programs that gives free cloud credits to researchers who are doing this not-for-profit work. So far, RoboBot and Split hasn't even cost us a dime. Yeah.
That's great. Thank you. And I think it's helpful to some of our researchers to know too, if they want to do similar projects or put them up online, let people use them, that there's resources there to maybe do hosting for free.
That's true.
Cool. Okay. I'm going to open the floor. Does anybody have any questions? Either in the chat window, or you can raise your hand, or you can come on the video and ask. Okay, I'm not seeing anything so far. I'm going to ask one of my questions that was from last time I saw the talk. So, and then maybe people might pipe up. So I noticed that the last part about bandits you were describing as fair reinforcement learning. So I was wondering, is it really reinforcement learning, or were you planning to extend it to like the full-blown reinforcement learning setting, or is it really just a bandit? Not just a bandit. I mean, I think it's really intriguing, but that's my question.
Yeah, so far it's for just bandits, but kind of that is the high level umbrella in which the multi-arm bandit problem lies. So the goal would be to extend this to the full-blown reinforcement learning setting for sure. And I know that you are also very interested in this, Graham. So I know that you asked me a problem about fair clustering last time, which I communicated to Evie, who was the main leading student author on that paper about fair clustering. And she has also had some interesting ideas about how we can define fairness in this clustering problem, when some people want the facilities to be away from them, some people want the facilities to be close to them. So we can chat about that later. But if you have some,
awesome. Okay, yeah, great. I'm really happy to hear you that you guys discuss that some more. Yeah, just for the benefit of everybody on the call. We're talking about, say, location of like a methadone clinic. That's like a classic example, which has come up when I was living in Toronto, or also living in Guelph, with like a transition facility of people that are, don't have stable housing. And then there's this common thing, like everybody says it's beneficial for society, but nobody wants it directly right in their neighborhood. So can these,
except for the people who really need it.
Except for the people who need it, right? So we're saying it's a little bit, it's related to the fair clustering, but it's beneficial to some, and maybe some people will resist it. So yeah, I really look forward to chatting. And if anybody else in Vector is on the call and interested in that problem, they should let us know.
Yeah, and we would also be happy to explore any kind of these kind of fairness notions in more general reinforcement learning settings or other settings.
Cool. Okay, any other questions out there?
So more of a policy level question. What do you think is the biggest impediment to, because given that machine learning algorithms are largely deployed by corporations, say Google or Facebook, what incentive do they have to implement fair algorithms if what they're doing right now is earning them a lot of money, and maybe regulations are really not there to kind of enforce these things?
Right. So I think, this is kind of a very broad question, and I wouldn't claim to have an answer that is any more informative than the people on this call. But one thing that I've seen is that these corporations really want to be ahead, at least the large corporations really want to be ahead of the curve, because it's in their incentive. For example, you might have heard this, that Facebook, Microsoft, Google, they all love GDPR, right? Because they are the kind of institutions who can actually afford to completely change their methods and make it GDPR compatible, whereas smaller companies wouldn't be able to do so necessarily, right? So these larger companies, they always want to kind of take charge in making sure that their methods are private, their methods are fair, and they in fact want to drive more regulation towards it. So that is kind of one incentive that they have. They want to be ahead of the curve. The other incentive is obviously happens when, so one roadblock to implementing fair solutions is that there are a lot of fairness notions going around in the community, and people don't really know when they should deploy which kind of fairness notion. And at some sense, you can also kind of criticize this work as proposing new fairness notions that could be applied to machine learning setting, therefore growing the pool of fairness notions that one might wish to consider. But as I tried to kind of comment, these are all the same fairness notions, right? So this group fairness that I mentioned earlier, it implies core and NB freeness and all of these other fairness notions. So these are all fairness notions that sit under this one umbrella of kind of preference-based fairness notions, where users look at other users and define kind of from their own valuation perspective. And if we can find a unifying framework for fairness that applies across all of these different problems, the same fairness notion that applies to clustering, that applies to classification, that applies to gerrymandering, that applies to resource allocation, if we can have the same fairness notion applicable to all of these domains, then maybe that would kind of reduce some of this roadblock, because then people can say, oh, here is the fairness notion that I want to apply regardless of the problem that I have. So you don't need to scour through like decades of literature in trying to find the exact fairness notion that is applicable in your particular setting.
I'm saying to Aaron, we should make a note for Vector's professional development curriculum, maybe a class on fairness and all these notions of fairness. I think this would be pretty applicable to our sponsors and collaborators in industry.
I feel like you volunteered to do the professional development. So if that's what you want to do, then.
Well, I don't know. I think Nisarg's the expert here. I'm doing the one on sort of math for ML. That's an advertisement out there, but you know, we do have faculty that are coordinating courses. I think one on fairness certainly would be of interest.
Right, and I think so. I know that Tony and Rich had a course, grad course last year on fairness, and I'm also planning to kind of redo. So I have a grad course which is on computational social choice, which looks at fairness, but also some non-fairness aspects, and the focus is more on kind of collective decision making. But I'm planning to kind of restructure the course so that it focuses on fairness and also incorporate some of this kind of fairness in machine learning work. But yeah, but I think fairness should like deserves more focus. It has gained a lot of focus in the research literature, but not in the academic world, in the kind of teaching world.
So what is your course, your computational social choice course scheduled for next winter, or when's the next time you'll be offering that?
This coming winter.
Oh, wow. Okay, yeah. Cool. You're gonna have about 50 people in the course now because you announced it here. Okay. Any other questions? If there's any students out there, actually, we discovered something at Guelph that was really beneficial to us, is that there's an Ontario visiting graduate student program. A lot of people don't know about it, but it allows you to take courses at other universities.
Oh.
They don't often advertise it, but a number of students have been taking advantage of it. You know, maybe not as important if you're a U of T student, because you've got a huge selection of courses.
Right, but yeah, that's something that I didn't know. I mean, I'm guessing that there would be U of T students commuting from elsewhere, and then when they are there, they would love to kind of take one course in Guelph or somewhere where it's close to their home at least.
Exactly. Like, it's really nice that there's this option that just opens up the portfolio of courses at all the Ontario universities to anybody. So yeah, OGV, Ontario Visiting Graduate Student Program. Check it out.
Yeah.
Okay. Anything? I don't see any other questions. So we're pretty much right on time then. So I think we'll wrap it up. So thank you, Nisarg.
Thank you for inviting me, and thanks everyone for tuning in.
Thank
Aaron,
you.
any last words from Vector?
No, I guess enjoy NeurIPS next week to everyone who's going. We have no talks next week because of NeurIPS. So if you're going, have fun and have a good weekend, everyone.